Back when you were taking physics for the first time, you probably learned about a fundamentally important kind of diagram called a free body diagram. This is a type of diagram we use for figuring out equations that relate forces on a body. Now, in robotics, we have an equivalently fundamentally important kind of diagram that is used for figuring out equations that relate positions and rotations. It's called a kinematic diagram. In a kinematic diagram, we draw a representation of how all of the links and joints are arranged relative to each other in a robot manipulator. Now, there are two kinds of joints that we can have in a manipulator. Prismatic joints, which allow linear motion, and revolute joints, which allow rotational motion. On your desk, you have one example of a revolute joint in this servo, and you have one example of a prismatic joint in this rack and pinion. A revolute joint always has one part, the rotor, which rotates relative to the other part, the stator. In a kinematic diagram, we draw a revolute joint like this. The cylinder represents the stator, which would be the body of this servo here, and the stick coming out the top of the cylinder represents the rotor, which would be the servo horn up here. Now, it's true that this servo's body is rectangular, and we drew a cylinder instead, but that doesn't matter in a kinematic diagram. In fact, there are three things that matter in a kinematic diagram. These three things are that 1, we get the type of joint correct, 2, we get the orientation of the joints correct, and 3, we get any offsets between the joints correct. I'll give some illustrations of this as we go. Now, since this is a rotational joint, the joint has an axis of revolution. The axis of revolution is a straight line around which the rotor rotates. In the actual servo, the axis of revolution goes right through this screw that is holding the horn onto the servo. If you turn the horn while watching closely, you will notice that every point on the servo horn rotates around the very center of the screw. In the kinematic diagram, the axis of rotation goes right down the center of the cylinder. Now, notice that there are two different ways that we could attach this servo to the board here. We could put it so that the axis of rotation is perpendicular to the board, like this. Or we could put it so that the axis of rotation is parallel to the board, like this. When we draw the kinematic diagram, it's important that we represent this orientation difference correctly. So, if I would attach the servo like this, then I should draw the kinematic diagram like this. However, if I attach the servo like this, then I should draw the kinematic diagram like this instead. Here, the square with diagonal lines represents the ground, or in this case, the board that the whole manipulator is attached to. For now, let's attach the servo to the board like this. To do that, pass 2 of these M3 screws up from the bottom of the board. And screw on these offsets here. Then place the servo on top of the offsets and use 2 more screws to attach the servo to the top of the offsets like this. pause the video while you finish attaching your servo to the board and then resume the video and we'll move on. Next, let's look at your prismatic joint. Later on in this class, we'll be attaching a motor with a pinion to this device to get it moving on its own. But for now, we'll just be actuating it by hand. We draw prismatic joints as a cube with a square next to it, showing what direction the joint can extend. For example, if I would orient the joint like this so that it extends up into the air and down towards the board, I would draw the joint like this. On the other hand, if I would orient the joint like this instead, then I would draw the joint like this. Now, we will be spending a lot of time in this class learning about serial manipulators. Serial manipulators are a type of robot arm that is made by attaching one joint to another in a series. Only one of the joints is attached to the ground. All of the other joints are attached to other joints. So, we can build an example of this type of manipulator by attaching our prismatic joint to the Revolute joint that we already have, like this. First, we'll attach a link to the servo to give ourselves a platform on which to attach the prismatic joint. Next, use two of the long M3 screws and two M3 nuts to attach the base of the prismatic joint like this. Pause the video while you finish this and then resume. Okay, now how can we draw this whole setup, this whole serial manipulator in a kinematic diagram? Here are some options. Which one of these do you think is correct? All of these diagrams shown here fulfill the first requirement of a kinematic diagram, that the type of joint is correct. All of these diagrams show a prismatic joint attached to a revolute joint, which is attached to the ground. But only one of these fulfills the second requirement, that the orientation of the joints is correct. In our actual build, the axis of revolution of the first joint is perpendicular to the ground, that is, the board, and the direction of motion of the prismatic joint is perpendicular to the axis of rotation of the first joint. These two diagrams aren't right because they have the axis of rotation parallel to the ground, not perpendicular. And this diagram isn't right because it has the direction of motion of the prismatic joint being parallel to the axis of rotation of the first joint. This diagram here is correct. Now, we haven't yet looked at the third requirement of a kinematic diagram, that any offsets have to be correct. To help us understand this requirement, let's change our build. Turn the servo to its 180-degree position, and then remove the base of the rack and pinion. Rotate the rack and pinion 90 degrees, and then reattach it. So what in our diagram needs to change now? We haven't changed the type of joints. We still have one revolute joint followed by one prismatic joint. And we also haven't changed the orientation of the joints. We still have the axis of revolution of the first joint being perpendicular to the board and the direction of motion of the prismatic joint being perpendicular to the axis of revolution of the first joint. But we've changed the type of offset that we have between the two joints. If we don't get this right in our diagram now, and we derive equations from the diagram and use the equations in our robot control code, the robot isn't going to work right. So here's how we draw the diagram for this robot. First, I move all of the joints so that they are in their 0 positions. We always want to draw the kinematic diagram as the robot is when all the joints are in their 0 positions. Next, I'll draw the first joint on the ground and label X and Y axes on my board and draw them also on my diagram. You should do this with me as I do it. Now I have to look at where all of the offsets are and what directions they're in. I have a vertical offset between the board and the top of the servo in the Z direction. Then there is an offset in the X direction. Then we have the second joint with its direction of motion going in the Y direction like this. Okay, now here's a challenge for you. I'm showing here a kinematic diagram of a slightly different manipulator. Can you build this so that your actual manipulator matches the diagram? Make sure you follow the 3 rules we talked about so that you have the right type of joints in the right order. The joints are oriented correctly relative to each other, and the offsets in the diagram match the offsets in the manipulator. When you think you have it right, put your name on the board under the Ready to Demo column, and I'll come over and check you off. Then make sure that you click on the quiz link and take the quiz for today.